Hello, welcome back. We have a new day. It's Wednesday, 11 a.m. I did fall asleep tonight with both computers on. My internet connection was super slow the last 2 days, but I did turn off my Wi-Fi modem and reboot. So now my internet connection should be normal. So now it's 11. Now I make this read lists, but that will take many days to read all this. But I think because I had to do a lot of work tonight, this morning, because I was uploading 15 videos and my computer was rebooting 5 in the morning when I was sleeping and stopped my upload. So when I wake up I have like 15 videos I have to put public, and some was not finished uploading, some was finished. So my morning was a big mess, but I have tried many times before. Now I just like to lay in my bed, relax. I need a break, few days from reading about tanks and wars and weapons. So this computer is calling looking at PC gamer hardware. Because I did start to read about computer processors and hardware and computer companies like Intel's on Wikipedia. Then I did find a lot more on Wikipedia I would like to read about. So, but I made a new videos. My video number 12,000 is called PC hardware. On these videos I will talk in English all kind of computers. I'll start to collect old computers. I collect old CPUs, Intel CPUs, AMD's old computer processors. And I'm collecting all the motherboards. I not have much, I only have 2 motherboards. And I will start collect the old Nvidia GeForce graphic card. I will start in the future to buy some I could put on my wall. I could have some old graphic cards and motherboards. I will put it on my wall for decoration, but I have to move out this apartment. I have to, because all these buildings is going to be renovated, so all tenants have to move out. They have to empty all base room. My base room is empty, so everything I own is inside here. All these boxes. So this is why my apartment look like this, because I have to get ready to move out. But I still need more boxes. I need for my comics and need some for my clothes, and I still got stuff, so I'm not ready, and all this need to go somewhere. All this need to be inside something. More clothes like there, more stuff there and there, everywhere. And stuff from my kitchen need to go into something. So all this from my kitchen need to go into some boxes, but I'm not going to move out today or next week. And then I got more everywhere. Inside here we got all jackets, clothes, shoes. Now the camcorder is out of focus, but a lot of stuff into here. And up here got a little bit then, but not so much here. I got some fine shoes I never use. That's some actually Sebago, some expensive, cost like $150. Sebago, but you're not walk. It's not good walking. This part is hurting your feet when you're walking. So that's not good for walking. When you walk, it hurts there. So I not use it. But I got it. Yes, and I got more stuff out here. Got more stuff there in this closet. Bed sheets. So let's continue. So, but that will take many days, and that's very complicated. All this computer processor technology. Now something did pop up. So let's get started. I need a minute to do myself ready in my bed. And I have to check my cell phone. Nothing there. So let's start read. So I will just read this my whole day. And when the camcorder is out of power, I will watch Star Trek on Netflix. So let's read about semiconductor device fabrication. I maybe read it before, but now I read it again.
Semiconductor device fabrication. NASA's Glenn Research Center clean room external image icon. Photo of the interior of a clean room of a 300mm fab run by TSMC. Semiconductor device fabrication is the process used to manufacture semiconductor devices, typically integrated circuits, ICs, such as computer processors, microcontrollers, and memory chips, such as NAND flash and DRAM, that are present in everyday electrical and electronic devices. It is a multiple-step photolithographic and physicochemical process, with steps such as thermal oxidation, thin film deposition, ion implantation, etching, during which electronic circuits are gradually created on a wafer typically made of pure single crystal semiconducting material. Silicon is almost always used, but various compound semiconductors are used for specialized applications. The fabrication process is performed in highly specialized semiconductor fabrication plants, also called foundries, or fabs. 1. With the central part being the clean room. In more advanced semiconductor devices, such as modern 14/10/7 nodes, fabrication can take up to 15 weeks, with 11-13 weeks being the industry average. 2. Production in advanced fabrication facilities is completely automated and carried out in a hermetically sealed nitrogen environment to improve yield. The percent of microchips that function correctly in a wafer, with automated material handling systems taking care of the transport of wafers from machine to machine. Wafers are transported inside FOUPs, special sealed plastic boxes. All machinery and FOUPs contain an internal nitrogen atmosphere. The insides of the processing equipment and FOUPs is kept cleaner than the surrounding air in the clean room. This internal atmosphere is known as a mini-environment. 3. Fabrication plants need large amounts of liquid nitrogen to maintain the atmosphere inside production machinery and FOUPs, which are constantly purged with nitrogen. 4. Feature size. A specific semiconductor process has specific rules on the minimum size, width or CD, and spacing for features on each layer of the chip. 5. Normally a new semiconductor process has smaller minimum size and tighter spacing. In some cases this allows a simple die shrink of a currently produced chip design to reduce costs, improve performance, 5, and increase transistor density, number of transistors per square millimeter, without the expense of a new design. Early semiconductor processes had arbitrary names such as MOS3, CMOS-V. Later each new generation process became known as a technology node, 6, or process node, 7, 8, designated by the processor's minimum feature size in nanometers, or historically micrometers, of the process's transistor gate length, such as the 90 nm process. However, this has not been the case since 1994, and the number of nanometers used to name process nodes, see the International Technology Roadmap for Semiconductors, has become more of a marketing term that has no relation with actual feature sizes or transistor density, number of transistors per square millimeter. Initially, transistor gate length was smaller than that suggested by the process node name, for example 350 nm node. However, this trend reversed in 2009. 9. For example, Intel's former 10 nm process actually has features, the tips of FinFET fins, with a width of 7 nm, so the Intel 10 nm process is similar in transistor density to SMIC's 7 nm process. Global Foundries 12 and 14 nm processes have similar feature sizes. 10, 11, 12, history. 20th century. An improved type of MOSFET technology, CMOS, was developed by Chitang Sa and Frank von Lassert Fairchild Semiconductor in 1963. 13, 14. CMOS was commercialized by RCA in the late 1960s. 13. RCA commercially used CMOS for its 4000 series integrated circuits in 1968, starting with a 20 micrometers process before gradually scaling to a 10 micrometers process over the next several years. 15. Semiconductor device manufacturing has since spread from Texas and California in the 1960s to the rest of the world, including Asia, Europe, and the Middle East. 21st century. The semiconductor industry is a global business today. The leading semiconductor manufacturers typically have facilities all over the world. Samsung Electronics, the world's largest manufacturer of semiconductors, has facilities in South Korea and the US. Intel, the second largest manufacturer, has facilities in Europe and Asia as well as the US. TSMC, the world's largest pure-play foundry, has facilities in Taiwan, China, Singapore, and the US. Qualcomm and Broadcom are among the biggest fabless semiconductor companies, outsourcing their production to companies like TSMC. 16. They also have facilities spread in different countries. Since 2009, Node has become a commercial name for marketing purposes that indicates new generations of process technologies, without any relation to gate length, metal pitch or gate pitch. 17, 18, 19. For example, Global Foundries 7 nm process is similar to Intel's 10 nm process, thus the conventional notion of a process node has become blurred. 20. Additionally, TSMC and Samsung's 10 nm processes are only slightly denser than Intel's 14 nm in transistor density. They are actually much closer to Intel's 14 process than they are to Intel's 10 nm process. For example, Samsung's 10 nm process's fin pitch is the exact same as that of Intel's 14 nm process, 42 nm. 21. 22. As of 2019, 14 nanometer and 10 nanometer chips are in mass production by Intel, UMC, TSMC, Samsung, Micron, SK Hynix, Toshiba Memory and Global Foundries, with 7 nanometer process chips in mass production by TSMC and Samsung, although their 7 nanometer node definition is similar to Intel's 10 nanometer process. The 5-nanometer process began being produced by Samsung in 2018.23. As of 2019, the node with the highest transistor density is TSMC's 5-nanometer N5 node, 24, with a density of 171.3 million transistors per square millimeter. 25. In 2019, Samsung and TSMC announced plans to produce 3-nanometer nodes. Global Foundries has decided to stop the development of new nodes beyond 12 nanometers in order to save resources, as it has determined that setting up a new fab to handle sub-12 nm orders would be beyond the company's financial abilities. 26. As of 2019, Samsung is the industry leader in advanced semiconductor scaling, followed by TSMC and then Intel. 27. List of steps. This is a list of processing techniques that are employed numerous times throughout the construction of a modern electronic device. This list does not necessarily imply a specific order, nor that all techniques are taken during manufacture, as, in practice, the order and which techniques are applied are often specific to process offerings by foundries, or specific to an integrated device manufacturer, IDM, for their own products, and a semiconductor device may not need all techniques. Equipment for carrying out these processes is made by a handful of companies. All equipment needs to be tested before a semiconductor fabrication plant is started. 28. These processes are done after integrated circuit design. Wafer processing, wet cleans, cleaning by solvents such as acetone, trichloroethylene and ultrapure water. Piranha solution. RCA clean. Surface passivation. Photolithography, photoresist coating, often as a liquid, on the entire wafer. Photoresist baking, solidification in an oven. Exposure, in a photolithography mask aligner, stepper or scanner. Development, removal of parts of the resist by application of a development liquid, leaving only parts of the wafer exposed for ion implantation, layer deposition, etching etc. Ion implantation, in which dopants are embedded in the wafer creating regions of increased or decreased conductivity. Etching, microfabrication, dry etching, plasma etching, reactive ion etching, RIE, deep reactive ion etching, DRIE. Atomic layer etching, ALE. Wet etching, buffered oxide etch. Chemical vapor deposition, CVD. Atomic layer deposition, ALD. Physical vapor deposition, PVD. Molecular beam epitaxy, MBE. Plasma ashing, for complete photoresist removal, historically done with a chemical solvent, to allow wafers to undergo another round of photolithography. Thermal treatments, rapid thermal anneal. Furnace anneals. Thermal oxidation. Laser liftoff, for lead production, 29. Electrochemical deposition, ECD. C. Electroplating. Chemical mechanical polishing, CMP. Wafer testing, where the electrical performance is verified using automatic test equipment. Binning and forward/or laser trimming may also be carried out at this step. Die preparation through silicon via manufacture, for 3-dimensional integrated circuits. Wafer mounting, wafer is mounted onto a metal frame using dicing tape. Wafer back grinding and polishing, 30, reduces the thickness of the wafer for thin devices like a smart card or PCMCIA card, or wafer bonding and stacking. This can also occur during wafer dicing, in a process known as dice before grind or DBG, 31, 32. Wafer bonding and stacking, for 3-dimensional integrated circuits and MEMS. Redistribution layer manufacture, for WLCSP packages. Wafer bumping, for flip chip BGA, ball grid array, and WLCSP packages. Die cutting or wafer dicing. IC packaging die attachment. The die is attached to a lead frame using conductive paste or die attach film. 33, 34.